we go. Okay, so we left off with partial fractions last time, and we're continuing with cool ways to find antiderivatives, right? Because remember the whole idea is that if you want to like calculate a definite integral, the easiest way to do it is with the fundamental theorem of calculus. Now, if you can rewrite a derivative rule as an antiderivative rule, you get your antiderivative. But sometimes that's not so easy. So we have like all these techniques for finding antiderivatives that are like more complex, right? We have like U substitution. We have integration by parts. We have trigonometric integrals. We have trigonometric integration. We have partial fractions. Like the list goes on. So the whole idea is that these are ways to find antiderivatives, right? When you can't just rewrite some derivative rule to give you an antiderivative rule. Okay, so there's another option available to you that's, or it's become available to you with the advent of computers. Oh my god, I became all small and tiny. Look at me. Does everyone like see me? I'm like super little. I'm small. I'm small, professor. Actually, it's super tiny. Like, what the hell happened? Let me fix that. Oh my god, I want to show you something for a little bit. Let me start it up. Okay, wait, wrong. I did that wrong. Okay, wait, what is going on? Okay, that is not what I wanted to happen. Okay, let's make this a little bigger. Yeah, I know I disappeared. We're gonna go back over to here, and I'm gonna turn on that one. Okay, watch. You know how like everyone loves all the Snapchat filters and stuff, so I've been like going around and like finding different programs that do it. So I've got my Matrix one. There's some really good ones. Can you imagine me like showing like this one? I think I'd like give people what's it called, but there's some really good ones. I like this one. My furnace in the background looks really cool in it. Does everyone see? And then I can like, oh look at my shirt like popped up. That looks so creepy. And then I can like invert the colors. This looks really bad. And when I go like this, I look like I'm a monster because you can like take out the teeth so clearly. There's actually one called Stoned. Watch this. I actually was using this one in a meeting. And actually a couple of people PM'd me like, can you please turn off that filter? It's really distracting. And I was like, no. So I left it there. And it looks really cool. Watch when I move. If you know, you know. I've got some other really good ones. Yeah, I know. Exactly. It's like, whoa. I've also got this one. This one looks really creepy. It's called Nervous. It like does this like glitchy look. like you're like yeah, it looks really weird. Oh, let's see, I've got another couple good ones. Oh, I've got these. These are always really fun. Imagine. Yes. I always love these. There we go. I can make my forehead really big. Yes. I've also got face detection. Just in case you needed help finding my face. There's a box around it. And then actually I really love this one. This one looks really cool. Like, it looks creepy. You can see my shadow in the background. Do you see like the shadow? Like, here's my hand. And then if you look very carefully, you can like see the shadow. There's some other really cool. This one actually looks really cool. It makes me look like I'm in a comic book or something like that. And then this one's really nice. I know, it's cool, huh? Alright, so we'll turn that off. There, wait, what the fuck? 1 second. There we go. Okay, I'm back. Okay, so back to this. There we go. Cool. Yeah, I had my fun for a little bit. So, one of the best ways to find an antiderivative, to be honest, is using a computer algebra system. So a computer algebra system is basically just the name for a computer program that does math for you. That does math for you symbolically. Yeah, I know. It's like, ooh, this sounds good. So there's a difference between computer programs that do math for you symbolically and a computer program that does math for you numerically. So we're gonna talk about the difference so that you can understand what's going on here. Okay, so let's say that you have a function f of x equals x plus 2. And let's say that you have another function g of x equals 5x minus 1. I don't know, I'm just making shit up. Okay. So let's say that you wanted to calculate f plus g of 3. So what I've done is I've made a new function that's the sum of these two functions, right? And then I'm evaluating it at 3. Let's just type that down. So what do I have here? So what we have here is a new function, the sum, and then evaluate at x equals 3. Okay, now there's several ways that you could go about this. To solve this problem symbolically, you would first take those two functions and figure out, well, what is this new function f plus g? So you'd say, oh, well, the new function f plus g is literally f of x plus g of x. So I'm working with the symbols. So then I would replace the symbols. What is f of x? Well, f of x is x plus 2. Well, what is g of x? 5x minus 1. And then what would you do? You would actually simplify this. You would say, well, I have the x plus 5x, that's going to give me 6x. I have the plus 2 and the minus 1, that's going to give me plus 1. Okay, so what we did here is we did symbolic manipulation. Does it make sense what I mean by that? I worked with the symbols to find my new function, right? I group-liked terms, things like that. It's really hard to have a computer do this for you. Does that make sense? If you had to write a computer program that would do symbolic manipulation, you would have to write the computer, oops, what did I do? I removed my spotlight. There we go, sorry. So, to do this, you would actually have to write a computer program to read in all the symbols and then program it so that it would do stuff with the symbols to simplify them, right? Does everyone get what I mean by that when I'm saying symbolic manipulation? Hopefully. Else? Okay, cool. Now, instead of doing it symbolically, what you could just do is do it numerically. So you could take advantage of the fact that, again, f plus g is just f of x plus g of x, which you know is just it's going to be f of 3 plus g of 3. And then you can just substitute it in right away. So you would say, well, what's f of 3? Well, that's going to be 3 plus 2. And then you can say, hey, well, what's g of 3? Well, that's going to be 5 times 3 minus 1. And the computer can go and calculate that, and it's like, oh, that's going to be 5 plus 15 minus 1 is going to be 14. And what's 5 plus 14? 19. So what's nice about doing the symbolic route first? If you first figure out that your function is 6x plus 1, you can now plug any x into there to get your answer, right? But if you do it numerically, do you see how this is not going to help me? Like, because I just plugged in 3 right away, that's not going to help me if I also want to figure out, well, hey, what's f of 4 plus g of 4, right? In other words, f plus g of 4, right? You're going to have to do the calculation all over again. Does it make sense that this calculation here that we did is not really going to aid us in this new calculation that I want to do? But if I do it symbolically, I can take my symbolic result and plug in 3 and I can plug in 4, right? Okay, so Wolfram and a lot of different programs that do symbolic manipulation like this, they're called computer algebra systems. And do you know what? Just because like I really geek out over this and I find it super cool, I'm just gonna like rant to you a little while about it because it's really interesting. Okay, so one of the first computer algebra systems was called Maxima. Why do you think it was called Maxima? Maxima. This was before the Macintosh was made. This was like made in the 1960s or so. The program's still around. But why do you think they called it Maxima? Yeah, they wanted to sound like Maxima. And basically they wanted a computer program that would like take a complicated expression and simplify it for you, or take a super complicated equation and solve it for you. And they wanted to do it symbolically. They didn't want the computer just to plug in numbers, like guess and check to find the answer. Does that sort of make sense? Like they didn't want it just to guess and check. They wanted it to sort of do what like mathematicians, what you do when you do your homework. You know how you write everything out and you cross and, you know, so you can see the work that it does. So tell me, people who know programming language, what are programming languages? What are some of the programming languages you know? Cool, Python, Java, some other ones. Throw them out there. Cool, C, C++, Ruby, Swift. Let's see, JavaScript. HTML is technically not a programming language, it's a markup language, it's not Turing complete. But why not? Any others? Got him! What else? Let's see what else you got. I'm curious if anyone has any more to add to this list. We'll find out our level of computer nerdom. Who will be head nerd? Rust, that's nice. A new type-safe C-like language. Lua, ooh, nice. Lua's a markup. Lua's a nice language. Haskell, Go. Oh, sweet. Go was made by the engineers at Google to like do a lot of parallel calculations. Oh, what do I do? I mean, to be honest, like I do a lot of programming in R because of statistics, and then I like Lisp, which is something that no one talked about on here. Lua is sort of inspired by Lisp. Who said Lua? Oh, John, nice. Lua's a good one. So let's talk about Lisp. Maxima was actually programmed in Lisp. And we're going to talk about like what Lisp does. Okay, so let's say that you're... How should we say this? What's a very common like language construct that you might use in Python? Or C, for people who program. Like, you know how like there's like all sorts of stuff built into the language to help you do programming? Like, I guess, let's just use an if statement. Everyone knows what an if statement is, right? So like in C, you could say something like, if x is greater than 0, bracket, you'll do something like x equals x plus 5, semicolon, and bracket, and then you could say then x equals x plus 1. Okay, so you have some number. What does this program do if that number is greater than 0? So like, what does this program do if x is greater than 0? Yeah, it adds 5 to it. Now, if you're dealing with 0 or negative, then what does it do? It adds 1. Okay, cool. Now, all of this and how it works is built into the language. Like, the people who created C wrote rules and said, hey, if you want to do an if statement, it needs to be written this way. What would you do if you wanted to change how the if worked? Like, does it make sense? Like, the if statement, it says, like, the way it works is they've set it up so that you have to say if, and then you have to tell it the if, and then you tell it to something to do, and then there's a then, and then you tell it something to do. Like, what if you wanted to change how it worked? Like, what if you wanted to say that there were 2 thens? Or if you wanted to make it so that you do all sorts of other weird things. Or actually, this should be else. My bad. What if you wanted to change how that worked? For people who have, like, programmed in C, is it possible to change how the if works? Yeah, you would have to write your own thing. And that's actually one of the problems with all these things like Python, Java, C, C++, Ruby, Rust, Go, Lua. We'll leave Haskell out of it because it doesn't have this problem. It's a lot like Lisp. It was inspired by Lisp. So if you wanted to change all of this, you would literally have to write a new programming language. Now Lisp, on the other hand, you can do whatever you want. The language is designed so that you can change the language in the program. And this fact, it's called being homoiconic. So if you ever take a computer science class, this is called a homoiconic language. It's because what happens is that the language itself, not only do you use that to give instructions, but the language itself can be used to change the language in the program. So this ends up being really useful because, like, if you were to try to go and use like C to write something that symbolically manipulates stuff, you run into all sorts of problems because you'd have like all these if statements or switch statements to like read in like your f of x. You'd have to like write a program so that it reads in f of x plus 2, and then it reads in g of x equals like 3x minus 1, and then you would tell it like, hey, can you calculate, give me what's f plus g of 3. So you'd have to like write all this stuff so that it reads it in, like groups the terms, does stuff like that, and it ends up being really difficult. Now Lisp, on the other hand, it's like designed so that like there's no distinction between the program about what the instructions are and what the data is. So like, it's sort of like you can write a program so that as it's running, it decides to change the code of the program. It's like a virus, basically. So this is like actually pretty cool. So there's my little side rant about that. No one really uses Lisp anymore. I mean, actually some people do, but like, it's like really hard to learn for a variety of reasons. And oddly enough, Wolfram was inspired by Lisp. The Mathematica thing that we use. It is a homoiconic language. Like in Wolfram/Mathematica, you can write a program so that it like changes how the program operates like at the source code level. So like, I guess here out of curiosity, who here are like computer science nerds? Like you're all into programming and stuff. Let's find out. I might not be preaching to the choir here, so I'm sort of curious. Do we have like people who are nerd out about this or not? Looks like no. I'm gonna end my rant about this. I'm in a second year, so I guess that counts. Yeah, it's pretty cool. Like the whole, like, I wanted to bring this up because there's a lot of research that's gone into this, and like it gives you an idea of like how hard, like there's this interesting connection between like the math and computer science, especially when it comes to stuff like computer science. When it comes to stuff like computer algebra systems, it's really hard to do this. And like if you can just sort of imagine like telling the computer to like simplify a problem for you, you might get like an idea of the difficulty of it. So let's go to Wolfram now, and I'm going to show you like what it can do for you in terms of all this. So let's say that I don't know, let's come up with a problem here. That you want to solve. You're going to be integrating from 3 to 5 of dx over the square root of x squared plus 4. And let's say you're looking at this and you're like, damn it, do you know what? Like, you're looking at it, you're like, I don't know what the antiderivative of this is. It's not really coming to me right now. And you're like, I think I could probably like solve this maybe using a trig substitution or integration by parts or something like that, but you're not really sure. Like Wolfram or any computer algebra system can help you out. So let's go over to Wolfram. Boom, here we are. There is a nice command called, surprise, surprise, integrate. And you can tell it like, hey, I'd like you to integrate 1 over the square root of x squared plus 4, please, with respect to x because of the dx. And boom, look what it gives you. It's like, oh, guess what the antiderivative of that is? It's the inverse of the hyperbolic sine over 2. Bam! So you can like use this to check your work always when you're finding antiderivatives. It's like pretty good at it actually. You can like just like throw all sorts of stuff at it. You can be like, hey, can we integrate sine cubed times cosine 3x squared with respect to x, and then boom, there it is. It tells you like, oh, the antiderivative of that is minus 3/8 cosine plus 1/48 cosine 3x plus 3/80 cosine 5x minus 3/112 cosine 7x plus 144 cosine 9x. Bam. And it's actually pretty nuts, like when you think about this. Can you imagine like having to like do that yourself, like with all the solving trig integrals and stuff like we did like a week or so ago? So it gives you a lot of, it helps you out a lot. So like you could just go back. Now we can go back to the notes. Well, we know that the antiderivative of this was the hyperbolic sine inverse of x over 2, right? So now you could just say like, okay, well, I'm going to do f of 5 minus f of 3. So you just see like, okay, hyperbolic sine inverse of 5 minus the hyperbolic sine inverse of 3. You plug that into your calculator, bam, you got an answer. I mean, that's really all there is to say about this section. This was section 3.5 in the book. Wolfram is really nice. Okay, so does everyone feel comfortable? You've got the integrate command on Wolfram. If you have a y value function, you could do like integrate, like, y squared, and then you put a y. So if you have like the antiderivative of f of y dy, right? So if it's dy, you have to have y there. Does that make sense? Like when you have the differential here, it tells you what you're taking the antiderivative with respect to. So you need to tell it what variable to integrate it with respect to. Alright. Mucho bueno. Alright. We're gonna move away from here. And now, because we talked about... So, well, actually, I guess I'm going to say one more thing. Wolfram is really impressive because it actually figures all this out symbolically. It doesn't just give you a number answer, it gives you symbols. Like, hey, the antiderivative of this is this formula. Like, it basically, like, sort of like... Actually, do you know what? There's a research paper I want to show you about this. Like, people are actually legit researching this still. Well, yes, but sometimes I want you to, like, tell it specific things. But yeah, Wolfram Alpha will do all sorts of stuff. Here, let me find the paper I'm looking for. Okay, so what these researchers did is, has everyone heard of deep learning? Okay, so deep learning is where you give it like a bunch of inputs with a bunch of matched outputs, and then the computer comes up with an algorithm to figure out how the inputs are connected to the outputs. So the inputs in this case were some function that you want to integrate. So if you want to integrate a function, the input would be the function, and then the output would be the antiderivative. So these researchers, they came up with a collection of a bunch of functions and their antiderivatives. And they fed this into a deep learning algorithm. So the whole point of the deep learning algorithm is that you want to be able to give it a function, and then what would it output? Like, what would it give you? Like, what is it learning to do? Like, it's trying to learn the connection between these two things. You gave it a bunch of functions paired with their antiderivatives. So you're writing a program so that you'll input a function, and then what will the computer spit out? What did it learn to associate the function with? The antiderivative. And like what they did is they went and they basically just gave this computer a bunch of functions and their antiderivatives, and then they started giving it new functions, and they wanted to see if it would be able to solve and find the antiderivative. And the crazy thing is that this program that they wrote was actually basically just as good as Mathematica in finding the antiderivative. So let me like share it with you. Okay, do you see this? So deep learning outperforms in Mathematica and Symbolic integration. So there's this paper, you can go read it. It's called Deep Learning for Symbolic Mathematics. It was done, let's see, how long ago? Let's find it on archive. It was published in December 2019. I remember when this came out. It was like pretty impressive. So like what they did is they found out, like they were able to show that like it was basically just as good as like doing integration as like, you know, the world's best technology at performing symbolic manipulations. So it's like pretty cool. Alright. So now we're gonna move on to doing this numerically. Okay, so we talked about symbolic integration. That's where the computer like actually manipulates the symbols to find an antiderivative. Now we're going to talk about numerical integration. So numerical integration is important because sometimes there is no antiderivative. Like there exist functions which have no antiderivative. Literally. So it's not like you're not trying hard enough. There just is no antiderivative for this function. So let's say that f of x has no antiderivative. And this actually happens quite often in physics and engineering. So if f of x has no antiderivative, and you want to calculate some definite integral with f of x, what is your only option to find this answer? Like, you can't use the fundamental theorem of calculus. Yeah, you have to, basically. So you're like, this just the only way to find this answer is to do the limit of the Riemann sums. some other method related to it. Okay, and that's what we're going to learn about in this section. Emphasis on the other method. So these other methods, we call them numerical integration. There are whole classes about this. Okay. So we're going to talk about those other methods now. So I'm going to draw a picture. Okay, so here's my x and y axis. So let's say you have some function f of x. Okay, and you want to integrate from x equals a to x equals b. And let's just do the example where n equals 4. So you can see my little points right here on the x-axis to make my rectangles. Okay, so remember what you need to do is you need to form rectangles. And then the area of each of those rectangles is f of x star times delta x. Now luckily delta x is constant, right? Because we split it up to equally partition the interval. Now you have a choice. You can decide to determine the height by going with the left endpoint. Alright, so does everyone see my left endpoint for this little box that I made right here? Now, what's unfortunate about my left endpoint for this example is in terms of it being an estimate. Like, what is not good about it? Like, why are we sad about this left endpoint for the height? Yeah, it's too small, right? Like, it goes under, so it's an underestimate. So I'm going to put U for an underestimate. Okay. And you can also choose the right endpoint. Actually, I'm going to change what my function looks like a little here. Okay, so we did a left endpoint. That's an underestimate. It's too small. Now let's do a left endpoint over here. Now what is wrong with my choice? Yeah, you're like, oh shit, now it's too big. Okay, and then you have some other choices. You can choose the midpoint. Usually that's pretty good. But it still looks like it's an underestimate. And you can choose the right endpoint. But in this case, that's an underestimate. Now, the idea here is that you hope that the underestimates and the overestimates balance out, right? So the hope is the under and overestimates balance out. Now, as n goes to infinity, what will definitely happen? So as like the number of rectangles gets really big, they have to balance out, right? But if you're solving this numerically, you don't have the option usually of just letting n go to infinity. You're just going to choose some large n, like, I don't know, n equals 1,000. And you're like, okay, well, I have to like eventually choose how many rectangles I'm going to have the computer calculate. Let's just choose n is 1,000. And the problem with doing Riemann sums like this is that for each of those little 1,000 rectangles, what if they're all overestimates? You're going to run into a problem because then the answer that the computer gives you is too big. Does that sort of make sense what I'm saying? Like if you had decide, if like your only way to calculate your definite integral is by having the computer estimate it with some Riemann sums, like worst case scenario is that all the rectangles are too big, right? They're all overestimates, which means that your estimate will be off by some amount and it will be too big. Well, yeah, you could get a more accurate estimate, but interestingly enough, there are like what they call pathological cases. There are functions where it's like, no matter what you choose, it's always going to be too big for like if you choose the right endpoint, and it's always going to be too small if you choose the left endpoint. And if you don't have enough computing power, you're not going to be able to get like a close enough answer. Does that sort of make sense? Like for like super complex functions that you would use, like that would pop up in engineering, like it takes like serious computing power to like get an accurate enough estimate. Now, obviously, that's becoming like less and less of an issue as like we get like stronger and stronger or faster and faster computers. But especially up until about 20 years ago, like this was like something that like people like were like, oh crap, we just like the computers, they're just not fast enough to get an accurate enough estimate. And even now, there's sort of an issue. So people came up with some rather ingenious ways to solve this estimation problem, and I want to like show you what they did. So actually, this was invented, the method we're going to talk about, this was invented, probably about 200 years ago. So it's called the trapezoidal rule. And there have been like a lot of modern takes on it. There's one called, let me give you the name. What is one of them called? It's like the RAF something rule. But like people are still researching this. So this is like probably like 300 years old. And there are like more complex methods, but let's just start with a simpler one. So let's say that you have your function and it looks like this. And you want to integrate from here to here. Okay, there's your x-axis. Okay, so let's say you don't have a lot of computing power available to you and you only want to use 4. N equals 4. Okay, so you're going to you're going to split it up. Say like you need to do this by hand. Okay, well that is not split up very well. Okay, the middle is like right here. Middle's like right there. Middle's like right there. Now, if you choose n equals 4, like if you choose a left endpoint, look at what happens. Actually, I'm going to copy this. Oh my god, this is genius. I'm going to use the same thing. I'm just going to copy it so you can like see all the different cases. So copy, paste. Oh my god, this is amazing. Look at that. Like now I just have like the same thing like there again. And let me paste another one. Oh my god, this is like perfect. Now I can just literally do the same thing and I won't have to just erase. So, let's say you go with left endpoint. It's too big. Left endpoint. Too big. Left endpoint. Too big. Left endpoint. Too small. Okay. And let's say on the other one you decide to go with right endpoint. Right endpoint. Too small. Right endpoint. Too small. Right endpoint. Too big. Right endpoint. Too big. Does it make sense? The question marks are like, it's just not covering that area. When I do little lines, that means I went over. So you're looking at this and you're like, well, maybe I'm sort of an idiot because I'm like demanding that like I only want to do 4 rectangles. You know, Matthew was just saying like, just why not increase the accuracy by adding more rectangles, right? But let's say I'm like, fuck that, I need to calculate this by hand. What am I supposed to do then? Because that was like the issue like 300 years ago, right? Like before there were computers. Like if you decided to do this numerically and calculate it, estimate it yourself, there was no one else to run the numbers for you. It's not like you could just pawn it off on the computer. So they came up with a pretty clever way to do this. So instead of drawing rectangles, they decided to have the shape be trapezoids. Okay, what makes something a trapezoid? So rectangles have 2 pairs of parallel, or 2 pairs of congruent sides. What makes it a trapezoid? One pair of congruent sides, yes. Or 1 pair of parallel sides, my bad. So this, for instance, is a trapezoid. And then you realize what you can do is, okay, the lengths of the sides will be determined by the value of the function. And then what I'm going to do is I'm just going to connect this point right here and that point right there, and that's going to give me my trapezoid. So I'm going to go from here to there. And actually, now that you look at this, how good is the estimate? It's not that bad. It's missing a little right here, right? Does everyone see how it's a little too small? But it's not missing much. And then you go to the next one, and you draw the top of the trapezoid like so. And actually, look, it follows it pretty well. Does everyone see how it's like, it almost, like the top of the trapezoid almost, let's zoom in, almost perfectly follows the function. And then you go on to the next one. Okay, this one's not as good. It's a little bit of an overestimate. Right there. This one was an underestimate right there. Okay, and then you go to the next trapezoid and you set it up. But this one's actually pretty good. It almost follows it pretty well. And what I want to point out is that if you zoom out, like this actually, even though it's not perfect, it's way better than what we got when we did rectangles. Like look, like if you look at the trapezoid example, this one right here and this one right here, they're like almost perfect. Does everyone agree? And then these two, like they're only off by a little bit. If you compare that with the rectangles above, do you see like how gigantic the overestimate is? Like the overestimate here is like tiny in comparison. So the reason the trapezoids work so much better is because they follow the function as it goes down and as it goes up. Right? With the rectangle with the flat top, it just stays at wherever the left endpoint was or wherever the right endpoint was, and maybe the function like goes down or goes up in between the two of them. When you decide to work with a trapezoid, it follows that. Yeah, sort of seeing it? Okay, cool. Okay, so let's figure out like how you would actually do this. Okay, so let's draw our little example that we're going to use to figure this out. Okay, so here's going to be my x-axis. Here is going to be my function. And let's draw one trapezoid. Going from right here to right here. And the top of the trapezoid will go from this point to that point right there. Okay, so let's put some dots. We've got a dot right here. We've got a dot right there. We've got a dot right here. We've got a dot right here. So tell me, how wide is this trapezoid? What's the length of the base? Yeah, so this is delta x. And let's say that this point right here is x naught, and this point right here is x1. How tall is the left-hand side? In other words, the length of that side is f of x naught. And then the length of the right-hand side is f of x1. Okay, now if you remember, the area of a trapezoid is 1/2 of the height times base 1 plus base 2. Okay, now usually the way we draw trapezoids looks like this. So this would be the height, and then the length up here would be base 1, and the length up here would be base 2. So what we've got basically is this thing on its side like this. So this would be the height. This would be base 1. And then that would be base 2. Okay, which means that the area of one of these trapezoids is going to be 1/2. Now the height in this case is my delta x. My first base will be f of x naught, and my second base will be f of x1. So I'm gonna, So we get a formula. AI is going to be 1/2 of delta x times f of xi plus f of xi plus 1. Right, because you're going to have a bunch of trapezoids, right? Remember how we did this with all the previous examples when you would set up the estimation? Right, you would get like a formula for like the area or the volume or whatever in each of the little pieces. Okay, so you can estimate the area of the whole thing. It's going to be approximately equal to adding up all of those trapezoids. So you're going to get the sum of I equals 1 to n of your AI formula, which is going to be the sum from 1 to n of 1/2 delta x f of xi plus f of xi plus 1. Now, what can I do to this formula? There's some stuff that I can like move around. Yeah, you can factor out the 1/2 and also actually one more thing, because it's constant because there's no I in it. You could also factor out the delta x. So you get the sum, or so you get that this is 1/2 delta x times the sum of, I will start at 0. I will start at 0 and end at n of f of xi plus f of xi plus 1. Okay, now we're going to look at this. Okay, so if you start by plugging in 0, you're going to get f of x0 plus f of x1. That's what you get when you plug in 0. And then what are you going to do? You're going to add to that what you get when you plug in x equals 1. Now if you plug in x equals 1, you're going to get f of x1 plus f of x2. And then you go to the next number. You're going to see what you get when you plug in x equals 2. So you're going to get f of x2 plus f of x3. And this will keep going until you get to end. The last one would be plugging in x equals n. Actually, n minus 1, my bad. So the last one will be f of xn minus 1 plus f of xn. Okay, now if you look at this, there's something really interesting that happens. So do you see how there's one f of x0? How many f of x1s are there going to be? 2. And how many f of x2s are there going to be? 2. And how many f of x3s are there going to be? 2. So what you get is 1/2 of delta x times f of x0 plus 2f of x1 plus 2f of x2. And you're going to have a bunch of things multiplied. You're going to have up to 2f of xn minus 1. And then you'll have a single f of xn at the end. So the reason in the formula you get all these 2's is because there's double from them when you plug it in, and there's only singles for the first term and the last term, because they don't double up with anything. And I think we're done. Did I go over? I apologize. Yeah, I went over. I'm just going to call it quits here.